All right, hi everybody. Welcome back to the DAC Pavilion. Nice to see at least some of you got back from lunch in time, so that's good. So our next speaker is going to be JP Fricker. He is the founder and chief system architect at Cerebras. So welcome, JP.
Hello, everybody. Hope you had a good lunch and you're not dozing off trying to digest. I'm just going to try to make this a little bit interesting for you and probably very different from what you might have heard so far. I'm going to walk you through an adventure we had with our company, trying to do something slightly different than most people do in the industry, and present to you a little bit the challenges. First, why we did it, and then also tell you about why we did it that way. And maybe you can then come to me and ask why for a couple of questions, and also maybe help us do better next time we do something like this. So maybe you don't know our company. Cerebras Systems builds systems. And we started the company to really develop a new class of products. We saw that the industry was using CPUs to train AI models, evolved GPUs, but even there we saw that there was an opportunity to do better. And we created a company to transform that, to transform the way we actually train networks. And we wanted to change the future of AI doing so, not just do one more chip that does slightly better than others, but actually transform the industry with that. Quite a high bar. And we were funded in 2016. We are now about 350 engineers. We have offices in a few places, Silicon Valley, San Diego, Toronto, Tokyo. We also have them in India now. And we have customers on multiple continents. So just to give you an idea, you've probably seen this before, so I'm going to use this as a backswing to get you to understand why we got where we got. But a few years ago, there were models that were of a pretty big size at the time, and we saw this evolve over time like crazy. Remember, the vertical scale is logarithmic here, so it's quite frightening to see this type of evolution when you need to solve a problem and you only get the hardware you get over years with a shrink, with a new architecture, maybe with a little bit of improvement that cannot sustain this pace. So in 2 years, having 1,800 times the performance need, it's frightening for design and system engineers because how do you get there? You cannot rely on just one technology or a technology node advances. You need to do a bit more than that. And so we saw this happening, and we saw this trend, and we haven't seen it tapered yet. So there is a fantastic demand, especially since people now understand that there is AI that becomes somewhat accessible. We have been working on ChatGPT-like networks for quite a while. We even published our own Cerebras GPT networks, which are publicly available. And so we have been in this field for a while, and we've seen this. So the industry has been using traditional techniques to solve this problem. For example, using a different technology node. So you go to a large foundry like TSMC, and you beg them to do their chip, and after year, you can get a better architecture. Yes, so you can do that with memory, you can do that with better precision in your architecture, you can do that with a better data path, so you can improve the performance at that, I would say, chip level by improving the technology and some of the building blocks of the mathematical compute entity that you need to use to solve and train neural networks. So with these approaches, you get about 2x with process technology and maybe a 3x with architectures or componentry that you can attach to your chip. But we need way more than that. So what the industry delivered was very small, only 2x on the process, 3x on advanced architecture, microarchitecture we call it, but we need 1,800 times. So how do you get there? So do you scale, just like put the same systems together to create big, large clusters? Well, that's how people have done it, right? So in the last 2 years, you get that microarchitecture on one hand, and then, okay, well, now you got that. How do you get further? You just scale out and create large clusters. Well, how do you get that amount of performance? It's not possible with the number of chips you would need to scale that far. So you would need so many chips that the scale-out solution would be impossible to implement. It's too big, it's too large. Too many chips to manage, too many chips to deploy, too many systems. The system themselves becomes too big to fit in data centers and to interconnect. So there are limits to that scale-out, right? The models need massive memory, massive compute, and especially massive communication. So one giant cluster of small devices, all of them come completely intertwined. You cannot really distribute the problem the same way. So this was not possible. You cannot really deploy very large cluster with very tiny chip interconnected at that scale, because the interconnection infrastructure becomes unbearable to implement and manage. Not to mention the programming level, which becomes very hard at the cluster level. So when you distribute these things, the interconnection becomes impossible. The programming level becomes very hard to maintain manageable. We need to solve it differently. So we need to be able, actually, because it's so hard to do, the actual effectiveness of what we got was about maybe 1 to 10x, as opposed to the 300x that we need. So we had to solve that in a different way. Not scaling with 10,000 GPUs, for example, but scaling in a different way, with a smarter way to get there. Right? Because that only gives you that 1 to 10x at the cluster level, plus the other improvement that we just talked about, only gives you a 60x gain. But we need more than an order of magnitude more than that. How do you do that? So we need to find ways to improve process gain, improve architecture gains, improve scale out. And we need to really balance these things, right? So what if instead of 2x, we were able to get 20 to 100x in process and technology? What if instead of 3x, you get 30 to 150x the architecture and microarchitecture improvement? And what about scalable? You actually get 300 times the capacity that you typically would like to get, but we were only getting about 10x before. To achieve that, you need to really think differently and think outside the box. So how do we really take advantage of, for example, amplifying Moore's law, right? How do we get better at taking advantage of Moore's law? So if you look at the size of chips, right? Historically, the chips became bigger and bigger and bigger. People tried to make bigger chips. It makes a lot of sense to pack more compute onto one chip, more memory onto one chip, more communication on one chip, and make them bigger because the infrastructure is cheaper within the chip than it is outside. So as you make them bigger, you have many challenges, right? You cannot really make it very, very big. The yield becomes a problem, the lithographic process becomes a problem, the thermal expansion becomes a problem, power and cooling become a problem. So how do you get there? So this is what people have been doing, right? They're trying to make the chip bigger while the chip cannot really be made bigger. The reticle size that you can get from a large foundry is limited, and you cannot really get bigger. So what do? Well, you step and repeat on something, like on a multi-chip module. So you put multiple chips on one MCM module, you get 2 and 5x in that area. You have now advanced interposer out there on the market, and people have done things that are bigger, maybe with 10, 20x the number of chips on one entity that's very small. We've done something different. We've done something very different. We basically created the WSE, which is a wafer scale engine, we call it, which is actually 56 times larger than traditional chips. And we did this, it's actually a full 300 millimeter wafer that's cut square. It has 2.6 trillion transistors on it, 850,000 cores. No, we don't program them individually. 40 gigabyte of memory on chip, 20 petabyte of memory bandwidth, and 220 petabit per second fabric bandwidth. And this is done in a 7 nanometer process, which means that we can still go further with better technology nodes and improve on this. This is what we are selling today, and I'm going to show you how we got to use this and why we got there. So first of all, you get a full wafer. Today, what people do, they build a wafer, and then, well, they need to test every die, and then they need to dice and actually remove all the die and sort them, test them, sort them, so that they don't use die that don't work. Well, on a die, usually, you get a couple of defects. And they're inevitable. You have them. But they're not large ones. They are usually small. But they can render your die completely useless. So what we did is to add redundancy to work around those defects. So we have a uniform, small core architecture that enables redundancy to address the yield at a very, very low cost, right? So we have multiple cores in an array, and we have a bit more of the cores than what we expose to the upper level software. And we have a fabric that allows us to reroute and basically remove from the logic level representation of the fabric the cores that don't work. So we have that implemented such that you don't have one core and another, and you have a one-to-one redundancy. You have many-to-one redundancy. And if you have multiple defects on your die, now you can work around all those defects while testing the chip and enabling configuration of that chip in such a way that exposes to the upper level software a pristine rendition of the wafer. So we can yield wafers now. Not only die, but actually a full wafer. So we can avoid having to cut the wafer and reassemble that to make a big chip. We can use the entire wafer as a full device. Right? To do that, we have to co-design. It's not done easily by just saying, well, we just do a chip that has redundancy. No, we had to interact with the foundries to understand what is the failure distribution, how the various failures are distributed on a chip, what is the size, their occurrence, and how many, and how to partition our chips so that we could always, most of the time, always get around those defects and represent a fully working system. Right? So in the standard manufacturing process, you take a wafer, you step and repeat a reticle on it, boom, 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 always the same. And then you cut, but there is a scribe line that separates every die. Right? So that scribe line is actually used as a mechanical barrier for die cutting and for test structures. So in those scribe lines, that is between two reticle area, usually you have a seal ring around the reticle to protect it, and then in the scribe line you have test structures. You cannot really go there. But what we did is actually implement cross scribe line connectivity. so in partnership with TSMC. And believe me, as a startup, going to TSMC and trying to tell them we want to make a big wafer scale, and trying to convince them that, yeah, this is what we want to do, and be more than 5 minutes in the room and not be kicked out. Well, that was a challenge, right? You cannot do that easily without having a really good story behind it on how you would do it. Because what they like to do is step and repeat and repeat and repeat and repeat. So they don't like to do something that's any different than what they used to, yet we were able to convince them that we had a good technology that required very few modification on their side and integrate in their process. So with this, we can extend the 2D mesh across the die. And we can actually extend across the boundaries that you usually have, the same fabric that we have inside the die across dies. So we don't have a bump in the road, we can just have a freeway across, and that freeway is just unimpeded from die to die. We had to do that with an extremely close co-design, again, between the fab house and the ASIC team and the physical design team on the chip. This is really hard to do if you just do a siloed design where you throw specifications around. You actually have to do a lot of co-design, intense discussions on what to do, how to do it, get the test structures away from where you need the wires to go. And that was not trivial. Now, what are the advantages? Well, plenty, and especially bandwidth across die, right? So by having many, many small wires, very short, it allows very high bandwidth at very low cost. They span only a few millimeters, actually less than a millimeter, and silicon area for those is very small, and the drivers needed for those are very, very simple. You don't need a SerDes that takes a lot of space and power. You can actually do this interconnection very, very efficiently. So you get an inter-reticle I/O that's pretty massive. Now, when you do this, however, so the on-chip bandwidth now becomes super high, very, very nice. But it shifts the complexity to the package. Now you have a nice wafer. Who do you go to get it packaged? Who do you go to actually make it into a system? By the way, a few kilowatts go to that wafer. I'm going to tell you more about that. So how do you do that, right? How do you package this thing? It's so big, you cannot even solder it to a printed circuit board or a substrate. Even the best substrate out there cannot really tolerate the interconnection you need, the power delivery you need, and having a thermal expansion that's compatible. So you cannot solder it. So we had to invent a connector that allows us to maintain connectivity for both power at high current and for signals to interconnect this. And the connector absorbs the variation of thermal expansion displacements that happens between the substrate and the silicon. Again, we had to do that in tight co-design with the ASIC team. So the packaging team had to talk very closely with the ASIC team to understand, well, where do you want the pins to be? How do they need to be? How many can we get there? And the type of connector was not just a traditional interconnect. This is very, very high-end interconnection, very small, very thin, and allows the connectivity for an entire wafer. Now that we solved the interconnection for signals and power, let's move out a little bit from the wafer and see what happens at the system level. Yeah, when you have an ASIC, a chip on your motherboard, and you want to power it, you can put a lot of power supply all around it. Well, when you have a chip that's that big, how do you get the current from the side of the wafer to the center? You can't. You need half an inch thick copper to get there. Remember, 20 kilowatts to a wafer, 44,000 amps into the wafer. How do I get that? right? That low voltage, the current is so high, I need so many layers of copper on the sides, I cannot really do that. So we had to solve it in a different way with using the third dimension. And this both for electrical distribution to the chip as well as cooling. So to distribute power to the chip, now I only have the surface of the wafer at my disposal. I cannot really bleed out because it doesn't get me much. I cannot get in. So the wafer is powered with vertical power distribution into it. All the power converters are not flat on the board. They're on the other side of the board, and they're using the third dimension for their design. Power converters usually take space. Well, we had to condense them, make them smaller, tighter, make them taller, take advantage of that height. As you make things taller and tighter, it's impossible to cool. You don't get any air through it, right? It's so packed that you need to use water now to cool it. For the wafer with 20 kilowatts, no way you can use air to cool it. At least you need to blow a lot of air to get there. You can't do that. So we use water to actually cool the cold plate, which itself cools the wafer. But to cool it, we cannot use something like you see here with airflow across the cold plate, right? We had to change the direction because as you go across, the air or the water warms up so much that by the time you get the other side, it's too hot. So for the water distribution, we also go and use the third dimension to provide that cooling effect. Now you can imagine that this is a lot of co-design with the system. So the package design of the chip is extremely tightly co-designed with the system packaging. All right. So here's how it is implemented in the system. Take the wafer, and we build something around it. So that's packaging the wafer, right? But you get the power on one side to enter the front of the chip. So you have one side of the chip, pretty much the entire more than 220,000 pins are actually powered by the front end section of the system. And then you have the heat on the other side. So you get two faces on the wafer, right? One for power in, the other one for power out. And the edges, that's where you get the IOs. All right, so here is an exploded view of it. Again, at the very front, maybe I have a laser pointer. Wonder is that? Yeah, this section is AC distribution. So we use this to distribute AC power. And we use power converters, AC to DC, to feed this board. Then we do use other boards to continue the distribution and reach these power converter modules here. So you can see the bottom one and the top one are power converters to power all the IOs on the chip, while the center here are power converters to power the core voltage of the chip, so all the logic. Then we can use these connectors here to provide power to those power converters. Power converters then feed the rest of the path to the wafer. And in the back, we have two I/O modules. You can see one on the left, one on the top, and a massive manifold for carrying water in and out of this thing. The large connectors on the side here are water connectors. All right, so put it back together. We call that an engine block. And that engine block is within a chassis. We had to put the chassis around. So as you can see, we started with the wafer. By the way, the wafer is not flat in the board, right? We had to put it vertical because to be able to power it, we had to put the power supply in the front. So I cannot put the power supply on top. I would have the power cord on top. And I need to swap power supply. So we turned it. We made the wafer vertical, and we had all the power supply in the front, right? On the side, you can see two power pump modules, a heat exchanger at the bottom, and you can see how the power can feed through the power supplies, reach the wafer, the heat goes in the back, The water in the system is carried around by the pump, and they actually flow the water into a heat exchanger that's at the bottom of the system. And 2/3 of the system is actually fans blowing air through a heat exchanger. We also have a version of this that's water cooled, so instead of having fans blowing air, you can actually connect this to a facility water equipment. All right, so this is the chassis. We made nice looking doors in the front so people can recognize it. Yeah, we like it. And this is an exploded view of the chassis. So again, you can see a lot of field replaceable units in the front here: fan module, pump, power supplies, the chassis itself, and the engine block, which is the core of the system. In the back here is the heat exchanger. All right. So this is built from the ground up, right? The system itself, the chassis itself, is built from the ground up to run a wafer scale engine. It's a single chip that's equivalent to 56 traditional chips. And combined with process strings, right, we can get about 20 to 100 times better performance by using this process technology. So by using a packaging technique and design techniques at the chip level, architecture level, to be able to use a wafer instead of a chip, we were able to get there. And again, leveraging the ultra high bandwidth and low latency you have on the wafer for connectivity. So this is like a cluster in one chassis, in one chip. So we already got a fair bit of that 1800x we needed with just this approach. So as you want to scale, you need to scale as a cluster. And we've done that. So we've put multiple of these systems in clusters now. We also take advantage of other techniques like sparsity to accelerate training models. So not just using dense models, but also add in sparsity to be able to accelerate that. And our system is tailored to take advantage of sparsity. So we can induce sparsity to take advantage of it in training models. So we can accelerate that even further. So we can enable existing and new novel sparse ML techniques with this approach. Both architecture within the chip, packaging that allows us ultra-high communication within a very large cluster scale chip, basically. It allows us to improve performance. And in the end, the system is actually the cluster, right? That is the accelerator. It's not the wafer anymore, it's not the chassis anymore, it's actually the entire cluster. And you still need to put them together. But when you do it smartly, you can actually get to the scale that is needed today to train these monster systems, so monster languages. So is this trend going to continue? Yeah. Is this possible? I bet it is. And I've been telling everyone since we started the company that, yep, you can do it. Yeah, you can do it. And I can tell you I have to repeat that a lot because every time we talk to a supplier, every time we talk to a partner, every time we have an investor, every time we have an employee coming on board, they come on board, they're a little afraid. 2 weeks later, they come to us, panic attack, I cannot do it, I cannot do it, I cannot do it. And then we have to walk them through and say, yeah, you'll see, you're going to make it, we are going to make it. We, as an industry, we're going to make it, I can tell you. But to do that, we have to architect things slightly differently, right? We need to co-design much more. We need to do things where we need to think outside what we're used to, outside what the industry have been doing all along, and use our imagination to go beyond it and not be afraid, right? We need to push beyond the flops with microarchitecture and thinking in a different way on how to solve the problems. And then cluster design. That's a massive problem because, well, a system will never be small enough to fit everything, even though you currently have one of those in your pocket too, right? I had one of these in a building of decades ago, right? So think about it. We're going to get there, but the demand will keep going. So we will have to architect those clusters also with imagination that goes beyond what we're used to. So that's it, and I leave time for questions because I believe maybe, hopefully, some of you have questions on this topic.
You mentioned that one of the hurdles might be the designing new clusters, right? It's a magnificent achievement and a breakthrough. But so how do you think you'll overcome that? And then you probably have to influence the server configuration architecture as well. So what do you see as a hurdle to unseat or take a little share from NVIDIA?
So if I take the example of our competition and how you make a cluster, if you need to put together 1,000 GPUs and you need to make them work as a cluster, you will see that together with the GPUs, you probably need to hire not the same number, but probably a good chunk of ML engineers and system engineers to make it happen. That's a burden. You want to train your model. You don't want to hire engineers to make it work. You actually want the solution of the training. And so the way you design is to facilitate the end user's task. So how you need to think about it is if you create clusters of many, many small pieces, as I said, the problem becomes exponentially complex to maintain. If you can design it such that you can scale linearly in complexity, in performance, in burden, there might be a way to actually keep going. But you need to be careful. You might reach a dead end there too, and we're going to have to innovate again. What we've seen with our approach is that we can scale linearly. So we don't taper after 10,000 or whatever number of GPUs becomes an insolvable problem. No, we can. So you just add systems next to each other. Because you compacted the system already by an order of magnitude or 2 orders of magnitude, you get an advantage there. You get a head start on the scale of the cluster because everything has been compacted one level. Now on the architecture of the cluster itself, there too, yeah, the cluster is different than what a cloud cluster might be, right? For serving web's requests, completely different architecture for that. You need more bandwidth. You need far more inter-node connectivity, so all-to-all connectivity starts to become a challenge. The type of switches you need is different. So the switching architecture, how you stack switches and how you create that switching domain becomes different. How you distribute the power, the memory, and how you deal with memory bottlenecks and bandwidth bottlenecks changes. So we have solutions. If you look at what we do, we have pretty darn big clusters now being deployed and used by our customers. Pretty happy to see that, but the challenges are still there. So I'm eager to work on those. Hope I answered the question. Thank you.
Very good presentation and impressive engineering.
Thank you.
And thank you for making my vision come true. In 1989, my PhD thesis was about a reconfigurable wafer scale integrated neural network.
Nice.
But I didn't have that many challenges to solve. One question is, how do you reconfigure the connectivity between the chips and the wafer?
So this is something we have to do during the entire lifetime of the wafer. From when you get it out of TSMC, you need to probe it, you need to test it. So we have tests that happen at that level. Every single step of the way, we can continue to do similar, and as we go and integrate more of the system, more advanced tests. All the way to the customer deployment, where there too we can test the same test. And we can actually identify which processing engines are faulty, which routing channels are faulty, and have an algorithm to reconfigure and provide a rerouted configuration and an abstraction for the system. So you need to stop the learning, training during that time. I get that. It's an event that you need to do, it's not ongoing, but it is ongoing in the lifetime of the system. It's like a maintenance. You do it, reconfigure. Right? Doing it on the fly might be possible, but require a bit more software. And we don't have the manpower at this time to actually do it on the fly. But it is programmable. It's not done with laser tweaking or electrical modifications. It's purely programmable, and we can program that in the field. Good?
All right, thanks a lot for the talk. Very interesting. Another Sabas from UCLA. So my question is, I mean, of course, the main motivation is making a big, chip to kind of run a huge model. But have you also thought about that potentially this could serve multiple users at the same time, being like a customizable, that like 10% is used by one user, like 50% is used by another user, and basically replacing the normal cloud. And if that's the case, have you thought about like how do you do multi-tenancy and stuff like that?
Yes. It's the first question that everyone asks when they see, oh, bigger chip can replace this cluster. I want to have so many more customers on this cluster.
Yeah.
Yes, turns out that there are so many more customers that want it all that doesn't matter that much at this time.
Okay.
Sometimes as a university, you could split it up that way, but actually splitting in time, it's a better way to do it for those small workloads. So we prefer to give for a university, for example, and we do that for free. You can actually get access to the system and use it for, like, instead of using it for a week for training your network, well, maybe you can do that in 2 minutes. So it's a way to partition, not in space, but in time.
Sure.
And it's actually pretty effective, especially when you start to go to a very large cluster. Imagine you have, tens of nodes, tens of systems clustered together. Do you segment one part of the wafer? It's actually, workloads are so heavy that people tend to train them for a couple of hours or days. Because so far, they had to train for months. And at the end of the months, they were still not sure it would converge, right? So that's where we play.
Okay, understood. Thank you.
Thank you for the talk, really great. Jen Lee, Future Technologies. Can you comment on for a community to learn from your effort, can you comment on Tesla's Dojo?
Yeah.
Like the differences, what we can learn from you guys' effort?
I love the guys at Tesla because we know them very well. We work together in different companies and we know them well. We actually talked to them at the very beginning of our company too. And very quickly we saw that they have a very different problem to solve. The problem we were solving was for a general market. The problem that we're trying to solve was really for internal purpose. And so it changed the architecture because of that. And it's different. They also have very big challenges. But remember, their density of compute is an order of magnitude smaller than what we have here. So the challenges related to integration are different. They really made it for a lot of I/O compared to compute. So the balance is different. The type of memory they have and how they place it and where they place it is different. And the way they scale is also slightly different. The type of network to scale it is different. The environment, the software to run it is very, very different. So this to tell you that depending on what your market segment is or your actual problem is as a company, solve a piece of the market, you tailor one area first. As a startup, you cannot really do everything at once. You tailor large language model at first, and now we go to computer vision as well, and HPC as well, because HPC for this, they love it. And we get, for HPC, for example, we get 2,000 times better performance on some problems. It's like amazing. So they are very excited. And for Dojo, they had challenges as well. But if you look carefully, you'll see that the density of what they have is far less. So the challenges were not as large. And so you don't get as much benefit of the integration. The bandwidth between those elements between the wafer is not as high. Right? Yeah.
Hello, thank you for the great talk. Excuse my question if it's naive, I'm new to this area, but it's if I understand, my question has to do with main memory. So you've got this giant wafer with lots of processor chips on it, but like where is DRAM and how do you connect that with sufficient bandwidth to all the the chips near the inside?
Remember the question about how you architect clusters? Well, there is part of that answer in there. First, we don't need as much DRAM locally because we have compute that's so fast that a little bit of SRAM very close is sufficient. And if you need to store something for a longer time, well, you might as well recompute because you have so much compute at your disposal. So in some cases, you just recompute what you would have stored for a longer period of time. So if you don't need as much memory for a long time during the processing of the network, you actually don't need as much on chip. Now, everything that's a little bit further away for us is like eternity. So a DRAM attached to a chip, it's too slow. It does not matter. I can as well use a network and put it somewhere on the server. And what is the best memory controller in the world? A CPU. Well, a CPU is the cheapest, fastest, easiest to use memory controller. So I can actually cluster servers with a lot of memory through a network because I've architected how I solve the neural network training problem such that I can move that memory anywhere on my network. And because I'm not latency sensitive for those, I don't care.
Okay, thank you.
Right? So I suggest, if you want more details, and my answer was very broad and high level, go into our website and look at how we do the memory X and swarm X architecture for the clusters. You'll get a peek of why. And there are some white papers on where we describe how the memory we have at our disposal, which is ultra fast, it's like a register access, allows us to circumvent the need for a lot of memory.
Thank you.
Hi, I'm Kenley from Georgia Tech. Thank you so much for the talk. Actually, our group have been trying to use the CS2 systems already on the cloud.
Oh,
yeah.
A customer.
Yeah. So my question would be more about the future. So as CS2 is already a huge improvement to CS1 in terms of the density and the on-chip memory. So what really would be the next step in your opinion? Do you want even a bigger wafer or maybe new technologies?
The obvious, easy, fast answer is follow TSMC. Okay, that's the easy one. Do the same form factor, same chassis. We went from CS1, I described CS2. CS1 was made in 16 nanometer TSMC, CS2 in 7, something else in something else. It's gonna come, right? So we have that. That's the obvious one. What is not as obvious is there another way to gain yet another order of magnitude by inventing something yet as different as this was? We did one miracle. We'll see if we can do a second one in this decade. It's actually very hard. Taking advantage of a wafer, single processing of one wafer at a fab is one way. If you want to make multiple of them, unfortunately, 450 millimeter wafers is just a dream, right? They're not there. If you want to do panels, yeah, you can get there. Now it's a reconstruction, because panels you need to reconstruct with multiple wafers. The precision that you need for manufacturing that is very challenging. So yeah, maybe into making bigger wafers. But remember, if I can scale linearly my performance with what I got today, maybe I can do something slightly better by using a similar approach, but optimizing where I currently have some bottlenecks, and not necessarily making an enormous wafer. Because at some point, yield matters again. And so it might not be sprinkle salt defects on the wafer that matters, but the actual assembly of such a large engine within a chassis. So you need to be balanced a little bit there. Even this is not easy. And if you go like a panel size, I wish, but the yields are a challenge there.
Thank you so much.
Welcome. All right. Thank you so much.